Hello, it's Jim from JetsonHacks.com. In this tutorial, we will build a web-based system monitor for Jetsons, which works on all Jetson models. We'll create several building blocks along the way, including a GPU activity monitor. Web-enabled applications are now an important part of the embedded systems world. One area we cover is WebSockets, which allow automatic updating and real-time communications between a server and client. Let's get started. On the Jetson Hacks account on GitHub, there is a repository named system-monitor. Let's clone the repository and switch over to that repository's directory. Scrolling down on the README, we can see that we need Python 3.10 or later. We are on a Jetson Nano here. We use Conda to create a Python virtual environment named WebEnv using Python 3.10. Proceed? Yes, please. Now we can activate our Python virtual environment. Let's scroll down a bit more. The requirements are in the requirements.txt file. This will install fast HTML for our web server and psutil to get system metrics. Let's do a sanity check and run Python 3.10. That's correct. Now let's get to work. Open up Visual Studio Code. Now open folder. It's system-monitor. Open Sesame. Open up the tutorial directory and we take a look at data_app.py. Clicking in the right-hand corner, we can select the Python virtual environment we want to use. We will use WebEnv, which we created earlier. The information we will be displaying is stored in files on the Jetson. First, let's get the name of the Jetson model we are using. It's stored in the file named model. Now we open up a terminal. Let's grab the file path. And we'll display the contents of the file. Here we see that we are using an NVIDIA Jetson Nano developer kit. Let's scroll down a bit. The amount of load on the GPU is stored in a file named load. Load is represented by a number from 0 to 999, which represents the GPU load times 10. In other words, percentage with one decimal place of accuracy. The GPU load is stored in locations that vary depending on the Jetson model. Since we're using the Jetson Nano, we'll use this path. You can see from this if statement that the GPU load is located in a different location on the Orin. In a major surprise, the GPU is not being used right now. Let's close the terminal. When we run the script, you can see that we print out the model name and the GPU load. We also have a function which we can call to get the GPU load. Let's run the script. We click the Run button. And there we go. That's not very satisfying. Let's run it again. Lots of GPU action here. One more time. Okay, now let's serve a web page with this information on it. We'll go to web_app.py. First, we import fast HTML, which is our web server library. Then we import the script we just went through. Then we instantiate the server instance. You can think of fast HTML as a domain-specific language. The @RT decorator denotes the endpoint. Then we define the function which describes the web page to return. In this case, we get the GPU load and then build the web page. It has a title of Jetson Web Sample. The body of the web page contains a div. The div contains an H3 header of the model name, and the GPU load is displayed below that. When we start the script, we start serving on localhost on port 5000. Let's run the script. Then we'll hop over to the web browser. Let's go new window on this puppy. Then we'll go to localhost on port 5000. And in about 40 lines of code altogether, we have our web server, which shows the GPU usage. Refreshing the page shows us the new GPU load. Let's close this up. Let me rearrange this. Modern browsers have built-in inspectors and debuggers. We'll inspect the page. Here you can see the HTML code that was actually generated by the description of the page. Now that we have our basic web page up and running, one feature to add is for it to automatically update. That's where WebSockets come in. What's a WebSocket? A WebSocket creates a persistent connection between a client and server. The connection is bidirectional and full duplex. That means you can transmit and receive data simultaneously between the two in both directions. Let's take a look at our WebSocket server code. Here's the import section. We import fast HTML and the WebSocket code from Starlet. Starlet is the web server that fast HTML is built on. We also import async IO to help handle multiple connections, and JSON. WebSockets traditionally pass data back and forth in a JSON format. Next, we create a set to hold the active WebSocket connections. In Python, a set is a hash table. Then we get the model name and the GPU load path, and our function to get the GPU load. Just as before. Update data is a function that runs in the background. It runs a loop. The loop gets the GPU load and then sends it to all of the active connections in JSON format. At the bottom of the loop, it sleeps for 1 second before starting all over again. Next, we define a string which we will add to the web page. The string contains the address and port of the server, which the client WebSocket needs to connect to the server. We also include the JavaScript file, which contains code the web page will need to use the WebSocket. The get function generates the web page. It's very similar to the earlier example. The not_string function will insert the string without any formatting. We add another div, which will indicate the connection status. We've given it an ID and class of connection-status. Now we take a look at WebSocket endpoint. The function is marked as async, which means it is non-blocking and can handle multiple WebSocket connections concurrently. It will be triggered whenever a new WebSocket request is made to the specified route. The first thing the function does is accept the incoming WebSocket connection. By calling await WebSocket accept, the server establishes the WebSocket connection and the client knows it is successfully connected. We add the connection to the active connections. Then the server enters a loop to keep listening for incoming messages from the client. The while true loop runs indefinitely while the connection is active. Here, when a message is received, it prints that message to the console. This is a toy example, but in a real application, you might want to take different actions depending on the received data. If we receive an exception, we exit out of the loop and consider the connection closed. This may be because the client disconnected. Finally, we do some cleanup, removing the connection from our set of active connections. And finally, on the next line, we bind the update data route to the WebSocket endpoint function. Last but not least, when the server starts up, we create a task to update the GPU data using the function we discussed earlier. The last line starts the server and we're off to the races. Enough talk, let's start up the server. Switch over to the web browser. I've found it best to open a new window or tab after starting or changing the server code. Let's open up a new tab and go to localhost :5000. It looks very similar to our previous example, but you notice that the GPU load changes occasionally. Let's take a closer look at the web page. We'll inspect the elements. Let's find the GPU load. You can see when the inspector is open that the GPU load changes a bit. It appears to be working. Let's go look at the JavaScript we put on the page. The JavaScript code manages the lifecycle of the WebSocket, establishing a connection and updating the UI with incoming data and visual feedback on the connection status. First, we grab the connection status element from the web page document. Then we create a new WebSocket from the host IP and port that was sent from the server. The WS: is the protocol scheme, which tells the server that a WebSocket connection is requested. The next two functions update elements on the web page to reflect the GPU usage and the connection status. Then we have the WebSocket event handlers. OnMessage event does all the heavy lifting. The event is triggered when a message is received from the server. The script attempts to parse the incoming message as JSON. If successful, it calls the update UI to update the interface with the new data. If parsing fails, an error is logged to the console. The onOpen message is triggered when the WebSocket connection is successfully established. The script logs a message and hides a status indicator indicating that the connection is active. The onClose event is triggered when the WebSocket connection is closed, either by the server or the client. It logs a message indicating that the connection was closed and calls update status to show the status as disconnected. The last message is onError. This event is triggered when there is an error in the WebSocket connection. We can also run WebSockets from Python code. Here's a simple example that simply opens a WebSocket, reads the data, and prints it to the console. The server must be running, of course. We import the Python WebSockets module. The rest of the code is pretty straightforward, much as we have discussed in other examples. Fire up a terminal. Then we'll switch over to the tutorial directory. For good luck, let's start up the WebEnv Python virtual environment. Then we'll run the WebSocket client script. And even more success. How are we going to live with ourselves? Control-C terminates the script. The takeaway here is that it doesn't take a whole lot of code to pass data back and forth between a server on the Jetson and a connected client. Let's talk a minute about web page presentation. As a developer, here's a few things that I've learned. Number one, use one font. You'll see a lot of developers stumble on this one. Using more than one font is a whole lot more work without much gain. Number two, keep it as simple as possible. It's like code in that respect. The more you add visually, the bigger the chance that it won't look as good as a minimalistic design. And it's harder to code. Deliver the most basic version as possible to start. Number three, to paraphrase Edward Tufte, only use the ink on the page to show the data. Be ruthless in your data presentations and make them as simple as possible. Again, it's easier to program and you have a better chance of delivering something useful. It works for Apple, why not you? Minimalism is your friend here. Think Swiss and Japanese design. If you build something for a larger group of users, you may need to design or have someone else design a better web page. Before doing that, define what a better web page actually means. Different web pages serve different audiences. Be mindful. We use a style sheet to describe the presentation of a web page, including elements like layout, colors, and fonts. CSS controls the visual appearance of web pages, allowing developers to separate content from design. Like HTML and JavaScript, CSS is a mature standard referred to as full-featured, meaning it's not simple to learn or apply sometimes. But it does tend to work, like billions of times a day. The code in our example is very similar to the previous one. We add a link to the font we are going to use, Roboto, which is a Google font. Then we add a link to our CSS file. The layout of the web page is similar. We add classes and IDs to many of the elements. I'll comment out the style sheet to see what the page looks like without styling. Let's start up the server and switch over to the web page. This looks familiar. Inspect the page. And we see not a whole lot has changed. I added a couple of elements to make it easier to style. Let's go back over to the server code, uncomment the style sheet. Let's make sure to save the file. When one of the pages in the server file directory changes, the server will restart. This will incorporate our change. Back to the web page. The moment of truth. We refresh the web page, and there it is. As you can see, quite a dramatic little change, all due to our little friend, the CSS file. Let's go look at our style file. This is all fairly simple. Each element has properties that you can set. For example, the body, which is the main part of the web page, has a background color, font, we use Roboto, and color of text. As you saw when we created the web page, we added class and ID identifiers. These names correlate with these CSS entries. CSS is expansive. This small example doesn't do it justice. Let me show you a different way to look at these properties. Modern browsers have built-in development and inspection tools. When you look at an element, you can see not only its assigned styles, but the inherited ones also. This is a great way of working with your style sheets, especially when you encounter issues. For many applications, this may be enough information for the user. However, here we will provide a graph which shows the GPU usage over time. We will graph the last 60 seconds of GPU activity. On the server side, the only real difference is that we have to add a place to show the graph on the web page. We do this here by adding a canvas element with an ID of GPU chart. We also add the chart.js library. Chart.js is a JavaScript library which is relatively easy to use. It provides a simple API to create various types of charts. As we go forward, some of the code presented is not as simple as it could be. That is because it is being prepared for when we have more system information to present. When we take a look at the JavaScript, you can see that things have changed quite a bit. First up, we create a place to store our charts. There's a major change in the update code. We get the current time, update the GPU usage percentage, and then update the chart. The chart data is implemented as a sliding window. We push the current time and GPU usage onto the labels and data set. If we have more than 60 elements, we remove the last one. We only keep 60 seconds of data. Then we have a function to create the chart. There are a lot of parameters you can use to configure these charts. You can read through these to get a feel for what they are. Let's scroll down a bit. Once the document loads, we create the chart. Chart configs holds the description of the chart. Then we use the create chart function we created earlier to instantiate it. Let's go back over to the server code and start the server. We'll switch over to the browser. And there's our flatlined graph. Let's get some GPU activity going. When I use the inspector, we get some GPU action. Let's open that up. We'll inspect the graph. That's more like it. A most useful tool is the JavaScript Debugger. Let's take a look at that. This will depend on the browser you are using. Here we go to Sources, and it's in the Static folder. We have a full debugger available to us. Let's set a breakpoint, and we can see that we receive data of 0. We can see the local variables. We can do all the standard debugging that debugging can do, including stepovers, all the good stuff. Take some time to check it out. If you are using Visual Studio Code, you can also debug the server. You have to restart the server in debug mode. Let's put a breakpoint here on update data. And you can see that it breaks here. Again, we can look at our variables and do all the debugging stuff that we know so well. Now let's take a look at the full System Monitor app. We import PSUtil, which we use to import system utilization metrics. We also import config parser, which we will use to read a configuration file which holds the server IP and port number. Next, we parse and read the config file. Set this to the IP of the machine if you intend to access it remotely. Here are the default settings. You would set your host to be the Jetson IP address. Next, we set up latest data. As you can see, in addition to the GPU percentage we were using previously, there are other system metrics which we gather using PSUtil. One addition is the connection manager. You'll notice that we still have the active connection set. Because we are working in a multitasking environment, we need to put a lock on the set when we add or remove connections to it. We also do this when broadcasting updates to all of the connections. And we have a method to remove any connections which appear to have wandered astray. Multiprocessing programming can be a little fussy at times. Let's scroll down a little bit more to update data. Here, you can see that we use PSUtil to get system information. Then we format it and put it into latest data. We then broadcast latest data to all active connections, then wait 1 second before doing it all over again. To help with debugging, we've added a route that returns just the raw system monitor data. Let's start up the server and look at it. Open up a browser window. And that's what local data looks like. The next function is the layout of the detailed memory chart. Then we start defining the main page. It's similar to our previous example. Here we add the CPU and memory chart. On the memory chart, there's a button which will display details when clicked. At the bottom of the page, we include our JavaScript file. Let's take a look at our style sheet. You might want to take a closer look. There's some animation code in here. Let's go to the JavaScript. It's very similar to our previous example. Last data mirrors the server information. Update UI is familiar. We add in the rest of the system information. The charts are in an array. It makes them easier to update. In the content loaded event listener, we add the CPU and memory chart. Then we have the button handling code. Then it's the same WebSocket event handlers. Let's go back and start up the server. Open up the browser. Not much GPU action going on. We can get more information by clicking the Info button. Let me resize it here. The font a little bigger. By clicking the arrow, we can go back to the other display. I will start up a video to increase the GPU usage, and that's a little bit better. Let's start up Jtop and get a quick comparison. Here are two different philosophies of data presentation. Jtop is great for very detailed analysis. However, you may want something a little more minimalistic, a little less overwhelming. The point here is to give you the knowledge to build your own tools. Leave a comment down below telling me if you like this level of presentation. As always, hit the like button and subscribe if you have not already. And thanks for watching.